This video is for Module 2, Part 3, and includes a discussion of the University of Pennsylvania smell identification test in regards to Parkinson's disease. All right, let's go ahead and get started. Many diseases or other medical conditions have an adverse effect on our senses. In some cases, the sense being affected may be obvious. For example, an eye disease may limit one's sight. In other situations, the sense of being affected may not be as obvious. For example, research has shown that the sense of smell is reduced in individuals with Parkinson's disease and also Alzheimer's, etc. The most widely used smell test is the University of Pennsylvania Smell Identification Test, commonly referred to UPSIT. This test was invented by Dottie, who is the director of the University of Pennsylvania Smell and Taste Disorder Center. This test is the gold standard in smell identification tests, and I've included a wiki link with additional information about this test. This video here shows how this test is used by the U.S. Army, and I will let you watch that. So a little bit more about this test. This is a 40-item test, so it has 40 questions on it. For each of those 40, an individual must scratch and sniff the odor. So they have a little spot here where the odor is hidden behind. I think you write on that with a pencil or scratch that off a little bit, and then you smell what odor is there. They give you one of 4 options for that odor. So Morley provides information regarding typical scores for the UPSIT in 2 different populations. He reported that on the 40-item UPSIT test given to patients with Parkinson's, the average score was 19. The average score from a matched control group, so a group that was similar to those with Parkinson's disease, so they were matched on things like age and sex, their score was 28. So now let's consider a couple of different research questions. Suppose a patient, we're just going to generically identify them as patient A, is believed to be in the preclinical phase of Parkinson's disease. Patient A is given the 40 UPSIT test, and suppose their score is a 19. So just suppose that individual scored something typical to a Parkinson's patient. Now let's consider 2 research questions. Research question number 1, does patient A perform better than an individual with complete olfactory dysfunction? So in other words, no ability to smell. Research question 2, does patient A suffer from some level of olfactory dysfunction relative to the control group? And again, that control group is known not to have Parkinson's disease. So we'll consider these 2 research questions here. So in research question number 1, we wanted to compare patient A against somebody that had no ability to smell. So the setup for that reference distribution is going to be number of trials is going to be 40, and the likelihood or chance of a correct response, again under the situation of no ability to smell, is going to be 1 out of 4. Recall that the individual taking the test has 1 of 4 options for that smell. So this is a forced choice test, but instead of having 2 options, they have 4 options. The number line for investigating research question number 1 is going to go from 0 up to 40. Again, there were 40 trials or 40 test items given. The no ability distribution is going to be 1/4 of the way up the number line. So the expected number here is going to be 40 times 1/4, which is going to be 10. So 10 is the expected outcome for an individual that cannot smell. The outcome from the study here is going to be 19. All right, let's take a look at the setup of the hypothesis, of the formal hypothesis test. So does patient A perform better than an individual with complete olfactory dysfunction? Our testable hypotheses here are going to be the H0, patient A has no ability to smell, and HA is going to be patient A has some ability to smell. So again, the research question is what goes in the alternative hypothesis here. So does patient A perform better than an individual with complete olfactory dysfunction? That implies that patient A has some ability to smell. The parameter here is just going to be the probability of correctly identifying the odor. And under a no ability to smell, that parameter value is going to be 25%, or 1 out of 4. This is a right-tailed analysis because the research question is asking, are they performing better than an individual? So that's a right-tailed. And the observed outcome here is going to be patient A was able to correctly identify the odor in 19 trials. So our first question here, what values are as extreme or more extreme than the observed outcome that will provide evidence for this research question? I will pause here and let you answer that question. Okay, let's use the reference distribution app to obtain a simulated reference distribution. And when doing this, let's use several thousand repeated outcomes. I'm not going to specify the values here. I just want you to use many outcomes so that that distribution is settled down quite well. So I'll go ahead and set up the reference distribution app here so that I can obtain my p-value. The probability of success is going to be that 0.25. Sample size is going to be 40. And I'm going to obtain 5,000 repeated outcomes here. Let's go ahead and obtain those repeated outcomes. Again, this reference distribution should be centered right around 10. And it looks like it is. The most likely outcome here is 10. This number line should go all the way up to 40, but the reference distribution app just kind of zooms in on the distribution for you. So my study outcome here is 19. And I want to count dots to the right of 19. So this is a one-tailed right analysis. So I want to leave that as greater than or equal to 19. And this value down here is my p-value. So I had 5,000 dots on that reference distribution, and out of those 5,000 times, 8 of those were at 19 or higher. And again, this reference distribution is under a no ability to smell situation. So that value that I got highlighted on the screen there is going to be my p-value. So I've given you some text boxes here to go ahead and answer 3 questions here. What is the p-value? What is your statistical decision? And then what is your conclusion? So I'll give you a moment here. You can hit pause on the video to answer each of those questions. Okay, let's take a look at the analysis for research question number 2. So here, what the research question was, is does patient A suffer from some level of olfactory dysfunction relative to their control group? So what I need to do before completing this test is understand how many correct what does the control group get, excuse me, how many correct does the control group get when they take this test? So if we go back up here, we have information of that by Morley here. Morley told us that the average score from a matched control group was 28. So some of these smells are kind of hard to identify. And the other thing that should be noted is that the older we get, our sense of smell is reduced. It also depends on what gender you are. I believe women have a heightened ability to identify odors compared to males. So for this matched control group, which if they're studying Parkinson's disease is probably an older group, their average score was 28. So if I take 28 divided by 40, that's going to produce 70% there. So the average amount correct for the control group was at 70%. So that's what I'm going to use to build my reference distribution for this research question. This research question, we want to compare patient A relative to their control group. So I'm not going to be comparing it against the 25%, but I'm going to be comparing it against the 70%. So that reference distribution is going to have the following structure. Again, it's going to go from 0 to 40. The expected outcome is going to be at 28, or 70% of the way up the number line. Again, our study outcome is at 19. So I'm taking this same patient and just comparing those using two different research questions. So the research question, does patient A suffer from some level of olfactory dysfunction relative to their control group? The alternative hypothesis then would be the individual has a reduced ability to smell relative to that control group. The parameter is going to be the same, the probability of correctly identifying the odor. The null hypothesis is going to be that they are similar to the control group or have the same ability. So the H naught here is going to be pi is equal to 70%, and the alternative hypothesis is that it has been reduced, so less than 70. So the type of test here is going to be left-tailed. Again, patient A has a total of 19 trials in which they correctly identified the odor. So I'll let you answer question 3. Move on to obtaining the reference distribution. Again, go ahead and use several thousand repeated outcomes when obtaining that reference distribution. So now we're going to set this up under probability of success is going to be 70%. We still have 40. Can obtain several thousand here. Now this test is a left-tailed test. If we come back up here, and it's a left-tailed test because I'm asking whether or not they suffer some level of olfactory dysfunction. So that ability to smell is going to be reduced. So here I'm going to want to switch that to left-tailed. And again, the study outcome is 19. Out of the 5,000 simulated outcomes that we obtained, in 10 instances, I had a value of 19 or less. So my p-value here is going to be 0.0020. Again, I'll hit pause here and have you identify the appropriate statistical decision and the conclusion. Okay, let us next consider the conclusions from the two research questions that we answered up above. So in these questions here, question number 5, which research question do you think is more meaningful? Research question number 1 or research question number 2? I'll let you go ahead and answer that. Question 6. Your friend makes the following statement. Patient A likely does not have Parkinson's disease because they have an ability to smell, as shown by research question 1. So I think the outcome from research question 1 is that patient A does have some ability to smell. So I'll let you go ahead and answer question 6 there. And then question 7 is asking about, well, what if I got a different p-value? So from research question number 2, the p-value that I got was 0.0020. Suppose instead that it was somewhat large. Suppose that it was 0.37. Okay, how does this change your prognosis that this individual may have Parkinson's disease? Does that influence what we believe there in regard to this individual's likelihood of having Parkinson's disease? Okay, one more example here. Example 2.3.2. Kurtz in 1999 discusses the malingering scale of the UPSIT test. The malingering scale is used to identify those people who are attempting to lie about their olfactory loss. So lie about their ability to smell. And here's just a snippet from their article. And I want to just point out the last sentence in this snippet. And that says that a score of less than 5 would be considered probable malingering. So I want you to use a reference distribution, again set up under a knowability situation. Number of repeated outcomes 5,000. So use that distribution to determine how likely it is that a person with no ability to smell would be identified as malingering. So in this situation, the UPSIT test would falsely accuse someone of lying about their inability to smell, when in fact they're telling the truth. So in a test like this, in a diagnostic test like this, we want that probability or likelihood to be small. We don't want to be falsely accusing anybody. So we'd like that probability to be small. So I want you to use the reference distribution app to obtain the probability of getting an outcome of 4 or less. So their malingering rule again was less than 5. So outcomes 4 or less would be identified as malingering. And I want to know how likely that is to occur in a situation where somebody does not have the ability to smell. So go ahead and obtain that probability value, and then you can answer questions 8 and 9. Okay, that does it for Module 2, Part 3. Thank you.